If you would recall, last week we were integrating rational functions and we talked about the three algebraic things that we needed to make integrating rational functions a thing. So specifically, we're talking about integrating a p of x over q of x, where p and q are polynomials. And we just wanted to outline some of the algebraic strategies that we can use to deal with rational functions. Specifically, why we didn't really care about any polynomials that were of degree higher than 2. So the first thing that we have, and this is the order that we would want to address them in. The first thing we look at is if we need to use long division. If the degree of the numerator is greater than or equal to that of the denominator, then we should use long division to go from improper fraction to mixed number. So when we're integrating rational functions, we want the degree of the numerator to be strictly less than that of the denominator. Remember our three core integrals for these techniques. Is degree 0 over degree 1. Degree 0 over degree 2 with complex zeros. And degree 1 over degree 2 with complex zeros. So here are our three core integrals. We only care about the degree when the degree of the numerator is less than that of the denominator, because we can always use long division to get to this scenario. The next thing we'll want to check if we need to use is partial fraction decomposition. If the degree of the denominator is greater than 2, 3 or above, then we'll want to factor that denominator and use partial fraction decomposition so that all the denominators are at most degree 2 with complex zeros. We also use partial fraction decomposition if the degree of the denominator, or sorry, if the denominator is quadratic with real zeros. In which case we'll take our denominator that's quadratic and break it into two terms with linear denominators. But this is as far as we need to go because we have the tools of long division and partial fraction decomposition. Okay. There are a few things that we didn't talk about in partial fraction decomposition. We just wanted to get the basic idea. We look at anything that's a factor. We try to factor the denominator. Every factor of the denominator produces a term in our decomposition. That's the way it works. Since we have already done the long division before we get to the partial fraction decomposition, in our decomposition, the numerators are always 1 degree less than the degree of the denominator. The last piece that we need is completing the square. This is in particular going to be useful when we have these arctangent terms in our integration. We want to look at variations of x squared plus 1 over x squared plus 1. So the next thing that we need to look at are variations on this x squared plus 1, 1 over x squared plus 1. That's what we want to look at today. Variations on our arctangent terms. Then we'll have a nice complete picture in how to integrate rational functions and the algebra involved. So this integrating 1 over x squared plus 1, degree 0 over degree 2 with complex zeros into an arctangent has a few variations. The first variation that we need to deal with is what happens if it doesn't say plus 1. So the first variation we need to deal with is integrating 1 over x squared plus something other than 1. The next variation on this arctangent business is the one that's going to involve the completing the square. That's what if there is an x term. Once we lock down these two variations and know how to deal with them, we are done with integrating rational functions. We can integrate any rational function. Just would require time and motivation. So the second one with the x term, this is the complete the square one. This first one, 1 over x squared plus a squared. There are two ways we can go about it. One, I'll just tell you what it is. So we're going to replace this old arctangent version with this new fangled arctangent. This is what's going to happen if we change that to something other than 1. So for example, if we wanted to integrate 1 over x squared plus 9 to x, that's going to be 1/3 arctangent x over 3 plus c. This is specifically degree 0 over degree 1 with complex zeros. Sorry, degree 0 over degree 2 with complex zeros. If the numerator is fooling around but still degree 0, then there's nothing really different going on. So if we change this to, let's say, 5 over x squared plus 9, this is still degree 0 over degree 2 with complex zeros. So we'll just end up with 5/3 arctangent x over 3 plus c. This is how we deal with terms that are going to throw arctangents our way. This is an arctangent thing. If we're not doing an arctangent thing, if we have degree 1 over degree 2 with complex zeros, then this is not a concern. This is for degree 0 over degree 2 with complex zeros. If, for example, we have 5x over x squared plus 9 to x. This is not, we're not worried about what the 9 says because we have an x on top. We've got degree 1 over degree 2 with complex zeros. This is a simple substitution. This is going to give us natural logs. So this one is just a regular substitution, W equals x squared plus 9. And in the substitution with the natural log, the plus 9 drops out. So dw is 2x dx. So a 1/2 dw is the x dx. We weren't doing substitution in the previous one. At least we weren't doing substitution w equals x squared plus 9. From a practical standpoint, we are done with this arctangent business. If you're still wondering why this 1 over a and the x over a, the x over a reveals exactly what we've done to come up with this variation. We went from 1 over x squared plus 1 is arctangent x, that we already knew, to 1 over x squared plus a squared is 1 over a arctangent of x over a. And we can see in the argument of our arctangent exactly what we're doing here. Make the substitution w equals x over a. So if we make the substitution w equals x over a, then dw is just 1 over a dx. So we could write this as a dw is just 1 dx. If we write x squared plus a squared and replace that with if we rewrite our x squared plus a squared in terms of w, then that would give us an AW replacing the x. I normally come at this from the other direction. I don't know why I started with this one this semester, and that's throwing me off. So I'm like, oh, dude, you went backwards from what you normally do. And I'm like, oh, it'll be fine. And then like, I was like thinking it's 8 o'clock in the morning. It is not going to be fine. And I could feel like the little swirly ball showing up, the little loading bar trying to fill up things as my ancient processor tries to kick on. So if W is equal to A over X over A, then that means that AW, oh, we usually did blue for our resubstitutions. That means that AW is equal to X. And then we'll see what happens when we rewrite the expression 1 over, I'm going to put the dx on top, x squared plus a squared. If I replace the x squared with an AW, and replace the dx with a dw, then we can just hit this with a little bit of algebra. Remember, the one that we know is 1 over x squared plus 1. That's what's going to give us our arctangent. So we're trying to make this a squared into a 1. Just doing a little bit algebraic sleight of hand, nothing up my sleeves. So if we rewrite the denominator, we still have our numerator of a dw. In the denominator, we have an a squared w squared plus a squared. And then from the denominator, I want to factor out an a squared. And that's the factor that we wanted, w squared plus 1. The integral of 1 over w squared plus 1 dw will give us an arctangent of w. But in the numerator, I have an a dw, and one of them cancels out, and that's where the 1 over a comes from. Okay. Then replace the w with x over a. So we can see what the substitution was by looking at the answer. 1 over a arctangent of x over a. We can see why that substitution works, because I want this a squared to be a 1, so I could use my core model. And we can also see where that 1 over a comes from. The most important part of this is that you all remember that the integral of 1 over x squared plus a squared is 1 over a arctangent of x over a plus c. Just remember that. That's the important part. But where this 1 over a comes from part is going to be important when you learn the integral of arc sine of a squared minus x squared. That's not going to have the 1 over a, and you're going to wonder why. This is what I'm going to remind you of. Because the integral of arc sine, the integral of 1 over a squared, square root of a squared minus x squared, that a squared is going to be hit with a square root before it comes out and cancels the a in the numerator. So, spoiler alert. Math class is just one big spoiler. You like walk in and instead of being surprised about how things work, I just fucking tell you how things work. Any questions? There's also the concern about what to do if there's something in front of the x squared. If there's a coefficient of x squared, factor it out. Let's deal with the x term. Then our training, or our instruction at least, on integrating rational functions will finally be complete, because I spend way too much time doing this. Oh, wait, that's not going to work. Make that a 4x. Four is terrible. Let's go with, let's put the 3 here. Much better. So the important thing to notice in this integral is that the structure is still degree 0 over degree 2 with complex zeros. That structure is still in play. We need to rewrite the denominator so we can do some arctangent business. So what we're going to do is we're going to rewrite the denominator by completing the square. We're going to think, what do we need to make x squared minus 6x a square? I want this to become x minus 3 squared. It's always going to be half of the x coefficient. What do we need to complete the square? So x squared plus 6x, we take half the 6, 3, square it, that's a 9. So I need to have a plus 9. I need a plus 9 to make x squared minus 6x plus 9 into x minus 3 squared, or the square of the difference of x and 3. So where we're going to get this plus 9 is from the 13. I'm going to split the 13 up into a plus 9 and whatever's left over. So we're just breaking up the plus 9 and whatever's left over is a plus 4. We're just rewriting 13 as 9 and 4. The 9 completes the square, the 4 is left over. We break the 13 up into a 9 and a 4. 9 to complete the square, 4 is what's left over. A lot of times when you're introduced to completing the square, you write a plus 9, then the plus 13, then a minus 9. Plus 9 and the minus 9 to balance things out. Excessive. And it's algorithmic. And it's process oriented. I would rather you understand what the purpose is instead of following some plan. So the reason for this is that we can rewrite this now as 1 over something squared plus 4. And now we can see an arctangent, degree 0 over degree 2 with complex zeros. The substitution would be to say W is x minus 3. dw is just dx. And this has the form 1 over x squared plus a squared. It's just shifted 3 units horizontally. Any questions? How's everybody? One last thing to come up because it's fun algebraic things of what if there's a coefficient of x squared on this one or on any other ones. I'm going to be super suspicious about it. Oh, using a square coefficient for the x squared, not just putting a 3 there. What we want is that x squared plus 1. We want to get that arctangent. We have the variation that's really easy to implement. 1 over x squared plus a squared. But both of those involve a coefficient of x that's equal to 1. So what I recommend that you do is just factor out the 25. This is really uncomfortable for a lot of students because you don't see the 25 as being a common factor. But everything's a common factor if you believe in yourself. We factor 25 out and we just have a 9 over 25. That's our a squared. It's fine. Everything's factorable if you believe it. All those things. This polynomial is not factorable. Every time you wrote not factorable on your polynomial quiz, you were wrong, and your teacher was wrong for allowing it. Unless you had previously established it's not factorable over the integers, I'm just kidding. Nobody was wrong. It was implied that you were factoring over the integers. That's why little man Tate was so wrong when the teacher asked, which of these numbers is divisible by 2? And he's like, all of them, in his little snarky, smart-ass voice. And he's like, oh, I'm sorry, little man Tate, that's a good effort. And I understand what you're trying to go for, but that's not what we mean by the word divisible. You're answering the question, which of these numbers can we divide by 2? In which case the answer is all of them. But 3 is not divisible by 2 because when we divide 3 by 2, we get a remainder of 1, which is not 0. You know what I mean? Has everybody seen that movie, Little Man Tate? I haven't even seen the movie Little Man Tate. But it's got this super genius kid and the schools can't handle it. And that is true. Schools cannot handle super genius kids. That's not what schools were built for, so I'm not sure what the criticism is. Do you know what I mean? Because every time there's a movie like where the kid is like some kind of super genius, some transcendent genius, they're like, oh, look how the public school system cannot deal with this kid. I'm like, oh, yeah, why would you expect the public school system to be able to deal with some transcendent genius? It's not designed for that. Why would you want to design a system that you're trying to apply to everybody to be even capable of dealing with the once in a generation kid that comes along? Just do something different. You know what I mean? Anyway, factor out the 25. Now we've got 1 over x squared plus a squared. We just got to be careful to see what our a is. The 1 over 25, that's the one that we factored out. A in this case is 3/5. So I need a 1 over a, which is 5/3. Arctangent. X over a, so x over 3/5 is going to be 5x over 3 plus c. So the 25 and the 5 will simplify, we'll get 1 over 15, arctangent. 5x over 3 plus c. Now that I've distracted you all with the concept of the super genius kid in school, and you're like all thinking, that's why I was struggling in elementary school. I was too smart for my school. Once again, we can see what substitution happened here to get us down to the x squared plus 1. If we make w equal 5x over 3 or 5/3 x, then that's going to turn this into an x squared plus 1. That's another way to look at it. Another way to deal with this is to just take this 25x squared. So an alternate method is to make w equal to 5x. And then dw is 5 to x. And we can see where the 1/5 comes from on top of the 1/3 from the 9. So good news. There's a lot of ways to approach this particular problem. Bad news. There's a lot of ways to approach this particular problem. If someone comes along and says, do it this way because it's fastest, just ignore them. Or if you want the snarky answer, just pull a Wolfram alpha and say, this is the fast way to not do this by hand. And say, we're not trying to get these done. We're not trying to get 115 arctangent of 5x over 3 plus c. Because if you just wanted the answer, if the goal was just to find that answer and you didn't have Wolfram alpha, your answer would be to ask someone who knows. That's how math gets done. The engineers don't have to do all their own math. They just hire a mathematician to do their math for them when it comes up. Do you know what I mean? How's everybody okay? What I'm saying is that the nature of education is changing. But the schools are very reluctant to change along with that. So here we are integrating rational functions, essentially for funsies. But there are a lot of ways to look at 1 over x squared plus 1 is arctangent of x. A lot of ways to deal with the 1 not being there and the coefficient of x squared not being 1. You've got to figure out which one is going to make most sense to you. I gave you the one that makes most sense to me. I have to imagine the 25 being factored out and making this a 9/25. One last weirdness about integrating rational functions. Here we have a rational function which is degree 1 over degree 2 with complex zeros, but we have a little bit of weirdness going on. We know what's going to happen to x squared minus 6x plus 13, because just 2 problems ago we completed the square, and that led to an arctangent. But that was degree 0 over this degree 2 with complex zeros. Now I've got degree 1 over degree 2 with complex zeros. And we saw on the previous page that degree 1 over degree 2 with complex zeros gave us natural logs. But we got the natural logs from degree 1 over degree 2 with complex zeros from substitution, and that same substitution is not going to fly here. If we try to do the substitution, w equal x squared minus 6x plus 13, then our dw is not present. The dw is 2x minus 6 to x. We're going to get a combination in this one. We are still going to complete the square with the x squared minus 6x plus 13. But that only helps. That's only going to lead to an arctangent term if I have degree 0 over degree 2 with complex zeros. So we're going to split this up. Notice that I have an x but this substitution that we use for degree 1 over degree 2 with complex zeros, the substitution that we use for that is going to need an x minus 3 to be the dw. So I'm going to make 2 terms. One of them is going to be an x minus 3 over x squared minus 6x plus 13, where the substitution could work. But I can't just throw a negative 3 into my numerator. I have to compensate. So I'm going to have one term. I'm just going to mark the numerator. That's what I want to be the derivative of the inside. But I can't just change my numerator. I have to separate, I have to balance things out. So if I write x minus 3, I have to, this still has to equal x. So I'm going to put a plus 3 to balance things out. And then my denominator can be the same, x squared minus 6x plus 13. And now I'm going to split this into two integrals with a distributive property. More algebra. One term is going to be the x minus 3 over x squared minus 6x plus 13. That's going to give us our natural log term. The other one is going to be 3 over x squared minus 6x plus 13, which is going to give us an arctangent term. So one term is going to look like this. And the other term is going to look like 3. This first term is going to get the substitution that we want to make. This second term is going to have a square completed. So this first term is going to give us a natural log. The second term is going to give us an arctangent. Thus concludes our 3-day foray into algebra. How's everybody okay? There's more that we can talk about as far as partial fraction decomposition goes, but we got the big parts. Factor your denominator. Each factor of your denominator corresponds to a term in your decomposition. The degree of the numerator in your decomposition should be 1 less than that of the denominator. Before that happens, long division has to happen so that you can make the assumption, so that it works, that the degree of the numerator will be less than the degree of the denominator. Now we've got this variation on the 4 arctangent integral. We are done with integrating rational functions. It should be noted that partial fraction decomposition does work if you have, say, a 5th degree polynomial denominator, and you break it down into a quadratic and a cubic. You can still do a partial fraction decomposition. You put a degree 1 over the degree 2 and a degree 2 over the degree 3. But you should never be in that situation because that degree 3 needs to be broken down somewhere. There's also what to do if we have powers. So if instead of just 1 over x minus k, we have 1 over the cube of the difference of x and k. So we didn't really talk about that. But that's okay. That was like 3 days of algebra. We can move on. Any questions? Comment? The reason that I like this is that the structure is so clean and it emphasizes algebra. It's really just these three core integrals and then algebra. And that's how we can deal with any integral of a rational function. Any questions? Comments? Usually this is when students start to be like, oh, dude, when am I ever going to have to do this? I've been upfront with you since the beginning about integration. You aren't. If you got a job and you're working on the mission to Mars and setting up a colony there, and you're about to do some integration by hand using trigonometric substitution that you learned in this class, you're probably about to get fired. Because your boss is going to be like, oh, dude, we have like millions of dollars of computers to deal with this kind of stuff for us. So don't be like, oh, I'm just doing this for fun. Or this is the way I was taught to do it in school. This is what I call the vampire rule, because in a vampire movie, you have to have a throwaway line right before the person who knows tells the audience what particular vampire rules are going to be in play. And the person in the know says something like, forget what you saw in the movies. And then they just outline the rule. They're like, oh, garlic, yes. Silver, yes. Sunlight, yes. Crosses, no. So whatever it's going to be. I'll just pick blade for an example. And it's the same kind of thing. Forget about what you learned in school. This is where we're going to do real. Any questions, comments, snide remarks? How's everybody okay? All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.